Hi, and this is just a brief introduction really to the A-level physics course. Really excited that you'll be joining us in September, so I hope you really enjoy what we've got to talk to you about today. And so this is just a brief introduction to the OCR A-level physics course that you'll be starting in September. It is a 2-year course. This is a brief introduction video to the OCR A-level physics course that you'll be starting in September. It is a 2-year course, and we'll get onto some of the information about what you'll be doing over the next 12-18 months going into your final exams in a couple of years' time. So, just as a bit of an introduction, I want to welcome you to NIA as a future physicist. My name is Mr. Broomhall. I am the Programme Leader for Science, as well as one of the physics teachers as well. Been a physics teacher for just over 5 years, and I cover most of the A-level specification, and I'll be teaching year 13 next year. We are really lucky to have 3 experienced teachers with the A-level physics course. We've got Mr. Urusu, who's the head of physics, and we've got Mrs. Gill, who will be joining our team in September. Physics brings together some absolutely fantastic mathematical ideas. It brings together topics such as electricity, magnetism, medical science, particle physics, quantum theory, but it builds upon your science education to make sure that you're able to think freely and speak honestly without having to rely on opinions of other people. As a new school, we don't have the data behind us in the same way that some other schools do, but we as a team in the department are really dedicated to making sure that your experience of physics is as enjoyable as possible, and we want to open as many doors for you as we possibly can. We want you to take the advantages, or take the opportunities that we provide to you before you leave our sixth form. It does give the school the advantage of it being new, of trying to do things differently to other schools. We're really hopeful of trying to get us a trip to CERN planned over the coming 2 years, which hopefully you'll be a part of, and building links with local industry, universities, and looking at all of the opportunities that are available because of doing A-level physics. Now, lots of people see physics as being very traditional as a subject and very academic, but over recent years this has really changed. Because of what we're living in at the moment, the world is changing. I never thought I'd be filming myself to do an introduction to A-level physics. We are suffering deficits within the world of people with analytical and problem-solving skills, which are absolutely core to the course that you'll do in physics. There's a huge percentage of the course as well which is dedicated to mathematical application, which you'll get marked up to 40% for, but don't let that put you off. The maths in physics allows a huge narrative to be followed of the history of the scientific concepts, including discoveries of the origin of the universe, the laws of motion, orbital periods of the planet, and the start of the electrical revolution. It shows us the observations in the real world and how they link to calculations to allow us as scientists to be able to predict what will happen in a given situation. In year 1, our physics course will enable you to build on your enthusiasm for physics, develop your understanding of fundamental concepts and building on the foundations that you already have, and things such as forces, motion, electricity, and introduce you to new parts of waves and quantum physics. You as our students will also have loads of opportunities to develop practical skills both through year 1 and year 2. In your final year, you as students will build on the knowledge of the laws of physics. You'll apply them to, or apply their understanding to solve problems on a massive range of topics, from things such as subatomic particles to the size of the universe. You will also have a massive opportunity of developing practical skills beyond what you've done through your GCSEs. Now, as mentioned previously, physics shares links to all types of industry. Most make the link of working in the engineering industry, but there are clear links of working in the NHS as a radiographer, working in banking or finance, and moving on to higher level education in things such as aerospace or acoustic technologies. Agriculture is also a massive growing area for physicists to go and work in. There are a wide selection of apprenticeship courses that are available from employers, and this is what makes A-level physics so valuable. The analytical skills that you pick up and practice through the 2 years of the course is what makes it so sought after when you're moving through to higher education. anyone can achieve within physics. I'm a strong believer in that, and it's regardless of whether you've come from a background where you've done combined science or whether you've done triple, but it's down to practice, and as long as you're dedicated to the practice, you will absolutely do above and beyond what you think you're capable of doing. Now, the course, you're going to be assessed in a way that you'll sit 3 exams at the end. It is a 100% exam. You'll be assessed on Module 1 all the way through the 2 years of the course, and it's where your practical skills are worked on. They're monitored by teachers, and you will complete at least 13 different practicals in which they, as practical activities, are monitored on by teachers. The exam board will visit at some point over the next couple of years to see whether they agree that your work and our marking of that is to a sufficient enough standard to show that you can do practical work within science independently and accurately. Module 2 is assessed over all of the papers and the exams that you'll do, and it is fundamental to the physics course. You'll start this in year 12, but within each of the modules you'll keep on picking up on things such as the quantities, units, and how to analyse data. Module 3, forces and motion, and Module 4, which is electricity, waves, and quantum mechanics, so quantum physics and photons, that's going to be taught in year 12. At the end of year 12, we're going to give you a full assessment to give a good indication of what you're capable of getting at A level after the 2 years. In your second year, you're going to look at forces in more detail, their effects within space. You're going to look at other things as well that you wouldn't have necessarily been taught before, such as simple harmonics, medical physics, and looking at imaging techniques such as radiotherapy. Now, we do OCR A-level physics, and the way that they structure their course is to encourage you as a learner to develop essential knowledge of the understanding of different areas of physics, how they relate to each other, and relate to things in chemistry and biology as well. We want you to appreciate or gain a deep appreciation of the skills, knowledge, and understanding of scientific methods that are required of you when moving further into higher education and into industry. And we want you to develop a competence and a confidence in a variety of practical, mathematical, and problem-solving skills that you will be able to apply in such a way that you won't doubt yourself. The course is assessed purely on end of course examination, as previously mentioned, but how things have been working recently is that there's going to be a greater monitoring of your work by teachers, as it could be that we may later down the line use that as part of a prediction of what you would have got in exceptional circumstances. Now, there are 3 assessment objectives. The first one shows examiners that you're able to work scientifically and demonstrate understanding of physics, recalling basic ideas that you're taught through the course. AO2 looks at your application of the ideas that you're taught by considering calculations, collected data, basically your data manipulation, and AO3 draws out how you're able to analyse and interpret data to draw conclusions. That is your practical part of the course, and that's where they will assess your understanding of the practicals in an exam. Your first exam will cover units 3 and 5, which is modelling physics. All of the topics on forces and space are covered in that. The second exam will be on electricity, magnetism, particle physics, and medical physics. Both of these assessments are 2 hours and 15 minutes long. Your final exam that you see will cover all of the topics we've completed over the entire of the course, and it will link together topics in ways that you may not have seen before. It's a very holistic paper of all of the course that we've covered so far, or over the 2 years. Practical part of the course is set as a pass or fail, and even though it doesn't contribute towards your final grade, it could determine on whether you complete the course or not. So by passing your practical endorsement, you will complete the course. Now, some of the things to give you a head start, there are a few books to have a look at. So all of the books here and the ISBN numbers are there for you to go and have a look at. The books themselves tend to start around £5 and go up to about 10 to 15. We do OCR A-level physics, as I've already mentioned, so getting the OCR A-level physics revision guide will give you a really good idea of the topics that we're going to cover. Head Start to A-level physics will bridge the gap between your GCSE and your A-level, and the essential math skills for A-level physics will support you in building your mathematical skills over the 2 years. Just as something that's a little bit different, a book that I really enjoyed as well about the ideas of physics is How to Teach Quantum Physics to Your Dog. You can pick it up second hand for about £3 or £4, but if you wanted it new, it's about £6 from Amazon. It's a really good place to get your head around some really quite difficult ideas that we do touch upon within the A-level course. And then finally, there's a few bits online that you're able to access free of charge. Isaac Physics you may have used at GCSE is a way of examining yourself on questions that are conceptual or show conceptual understanding. A-level Physics Online and the YouTube channel Physics Online, all of the videos are relevant to the course that we do. And then finally, if you wanted to go through the entire of the course in 7 hours, there is a line of videos called Crash Course in Physics, which again are free to access through YouTube. So, looking at what we wanted to cover before starting in September, vectors and scalars are one of the most basic starting points within physics. When we're talking about vectors and scalars, we're talking about physical quantities. We're talking about things being scalars, we're talking about things being vectors, and vectors may be something that you've come into contact with not just in science but in maths. When we're talking about scalars, we're talking about magnitude. How big is something? Whereas vectors, we're talking about the magnitude and direction. How big is something and what direction does this go in? We'll look at examples of each, and then you'll be left with some questions to take away and complete, which you will bring along to the first part of your physics lesson. So what we're going to look at in the next 10 minutes or so, 10-15 minutes or so, is anything to do with the difference between scalars and vectors, and showing you how to draw scalars and vectors within a force diagram. We're going to have a look at how to find resultant vectors and calculate a resultant force on an object, which is key all the way through the course. And if you really wanted to go and stretch yourself, be able to try and work out the size of a force on an inclined plane. So if you've got two forces or two vectors, that are acting at angles to each other. Now, when we're talking about scalars and vectors, there are very specific definitions for them. A scalar is any physical quantity that is not directional. For example, mass or density. There's not a negative to it. There's no negative energy, there's no negative speed. There may be a negative velocity though, and this is where the difference comes in. A vector is any physical quantity that has a direction and a magnitude. So we can have negative forces, or forces that work against each other. We can have a negative acceleration, where an object is still moving forward but maybe slowing down to a stop. A car, for example, coming to a set of red lights. A vector, when we're talking about physical quantities, is something that has a direction. Now, if we look at this treasure map, we've got the road, which is a dotted line, and then we've got the walking path, for example, that is taken from the dot to the cross. Now, the distance between the 2 points, our displacement there, is represented by how far between the 2 points and what direction or a bearing value. Whereas if we look at the route by road, which is represented again by that dashed line, it will be much further to have travelled, and that's where we start looking at the difference between distance and distance covered and displacement. So here, a displacement vector is looking at the closest distance and direction between them 2 points. If we were to look at vectors and how they're applied, we can look at things such as force, or we can look at acceleration and velocity. If it doesn't have a direction, or a physical quantity that we're using doesn't have a direction to describe it, that's when we start looking at scalars. Now, when we look at scalars, the most common ones are mass. We don't have negative mass. Density, we don't have a negative density. Volume and energy, all things that can't take up a negative space. So energy not being negative will mean that we can't get energy from putting nothing into it. Looking at how we can use vectors and adding them together, we can look at the size of both of them and put them together to get an overall magnitude. Now, if two vectors are of the same type, we can add them together, but we need to be careful. If we're looking at two vectors, one force and one velocity, I can't add them together. If we're taking velocity and velocity, for example, I can add them together because they're in the same units. Make sure that their directions are coming as a bearing from the same point, because the difference in their directions might mean that simple addition isn't possible. but we can look at an example of that later on. Now, the most simple method of looking at the size of a vector is to use a scale diagram. So, for example, if you walk from A to B and then B to C, as shown by this graph here, then your overall displacement is going from A to C, and that's how you'll see it normally represented within maths. If two forces are parallel or acting along the same plane, then they just add together, and that's what you're expected really to do at GCSE. Opposite directions would have opposite signs, and that's where we start looking at taking forces away from each other or cancelling forces out. Now, we can look at something which is slightly more complicated. If we've got two force vectors that are acting on an object here, we've got force A and force B, the total force will be the addition of force A and force B together. This is where we take something called the top to tail method, where we take the top of one arrow and put it to the tail of another arrow, and then join together the tail and top of the two arrows added together. That gives us line C, and that will show the overall force C which is acting on the object from the start point. Now, in maths, especially if you've done higher, the approach is to look at something called Pythagoras. Now, the same answers, or you will get the same answers from these, and as you move through the course you'll be looking at using sine and cosine rules, which are provided to you in your exam, so you won't need to remember them. Now, using trigonometry, a squared plus b squared is c squared, that is going to save you a lot of time in making sure that, but you have to make sure, that things are at right angles. If not, you can't use Pythagoras. Knowing the sum of the squares, though, is or knowing that the sum of the short sides is equal to the square of the hypotenuse or the long side, means that any two vectors acting at right angles to each other can be really quickly added together, really quickly determine the size of them. So here, there's going to be an example question. An aircraft will fly 11 kilometres north and then 11 kilometres east. What's its displacement? If I wanted to take the approach, the mathematical approach of using Pythagoras, a squared plus b squared is c squared, I would look at the directions of the two arrows, 11 north, 11 east, or 11 kilometres north, 11 kilometres east. I know that a squared plus b squared is c squared, and both of them are 11, so 11 squared add 11 squared will give me my resultant, or r squared. 11 squared is 121, and added together, or doubling that, it give me 242. To take the square root of that will give me the resultant, which in this case is 15.6 kilometres. So the displacement is 15.6 kilometres. We could also look at taking a vector and splitting it into its two components by looking at the angle that is formed between the overall resultant vector and either the vertical or the horizontal component. You always need to make sure that your calculators are in degrees though, because if it's in radians or gradians, you will end up with a different answer. Radians and gradians are just two different ways of calculating angles, and radians we'll use quite often when looking at waves and circular motion, and gradients is a method that's not really used a lot anymore, but it was initially invented to try and make 100 gradients in a circle, almost like making a circle metric. Now, to split these components, I know that I've got 5 cos 53 degrees by using SOHCAHTOA. I know that I'm looking for the value of the adjacent to the angle by using the hypotenuse as 5. So I know that when I look at my horizontal and my vertical, by working them out, I'll find out the distance the ball has travelled up and across. So vertically it's travelled 3.99 metres and horizontally it's travelled 3.01 metres. So just in summary, before you have a go at the worksheet that's been set, scalars themselves will only have a magnitude, something like mass, density, something that can't be negative. Vectors will have a magnitude and a direction, something like velocity for example. An easy way to remember the difference between scalars and vectors is speed can't be negative and is a scalar. Both speed and scalars start with s. Velocity, on the other hand, can be negative, and vectors also represent a direction, so must also take negative values. Velocity and vector both begin with v, and that's how I try to remember the difference between the two. If we're to add vectors that are in different directions, we need to make sure we're using accurate scale diagrams, or if we're lucky enough that the vectors are at 90 degrees to each other, it can be done by using Pythagoras theorem. Any vector can be split into two perpendicular components, or at 90 degrees to each other, so we can work out the vertical and the horizontal component. Using each of them points and the examples that I've gone through, feel free to go backwards and forwards through the video as you need. Have a go at the questions that are on the worksheet that you'll be able to download from the NIA website.